I'm Wen Ruidiao, a PhD student coming from the Chinese University of Hong Kong. It's my pleasure to introduce my work on Android security. It's a joint work with Xiangyu Liu, Zhou Li, and Kehuan Zhang. The topic is no pardon for the interruption new inference attacks on Android through interrupt timing analysis. Nowadays, smartphone plays the important role of personal assistant and data container in our daily life. Different from the traditional desktop platform, mobile platform have to meet the new requirement of mobility and usability with limited computing resources. Therefore, new specialized hardware components are introduced, like camera, GPS, NFC transmitter, touchscreen, and accelerometer. Previous research investigated the security threats coming from particular hardware component, and most of the tech focus on reading data directly from sensors. But one question is never answered. What about the security implication of the integration of specialized hardware and the tailored kernel? Android is built on the Linux kernel and inherits the interrupt mechanism from Linux, which is an efficient communication method between CPU and the external devices. All reported interrupts are counted by the OS and saved into a system file named proc/interrupts, which is public to any process. We find such interrupt statistical information reflects the real-time running status of devices, which could be exploited by an attacker to infer sensitive information, such as user-sensitive data and interaction with the device. So our answer to the previous question is, through analyzing the time series of interrupts occurred for a particular device, user-sensitive information could be inferred without any permission. The root cause of this new security threat comes from the ill-convinced integration of specialized hardware container and the tailored kernel. Actually, previous research have mentioned the potential privacy risks related to interrupts, but none of them present concrete attacks. However, the development of modern smartphone platforms offers a new alternative to exploit it, because new hardware components are introduced, and most of them could interact with the user directly and brings new kinds of interrupts. That is new attack surface. Next, I give some basic background. Hardware interrupt mechanism is purposed to enable timely event management. If an external device requires the immediate attention from the OS, it will emit an electronic signal called interrupt request and send it to the programmable interrupt controller, or PIC. PIC will notify CPU to process this request immediately. In response, CPU will hunt the current execution thread and evoke the rejected interrupt handler to process it. Such a process alerts the current execution thread is called interrupts. After the processing is completed, the reserved context is restored. The hunted execution is resumed. This picture shows an example of public interrupt statistical file captured from Nexus 6. In the circled part, it shows how many interrupts occurred from the starting of the system. Each counter corresponds to a different kinds of interrupts. So the counter at 1 means interrupts occurred, that is a new event coming. Through monitor the interrupt time series of such file, user sensitive could be inferred. We call it interrupt timing analysis. As showcases, I will give two concrete inference attacks against the user's unlock pattern and the foreground application using our proposed interrupt timing analysis. The first attack to infer the unlock pattern. Touch screen has become an indispensable component for nearly all smartphones. A large amount of user-sensitive information passes through the touch screen, such as text messages and the unlock pattern. Unlock pattern is incorporated into Android as an alternative authentication method to overcome the traditional the usability issue from the traditional text-based password. When user want to unlock his phone, a 3 times 3 matrix will be displayed, and the user has to draw a pattern through swiping lines that connect dots in a certain order. Also, each order could map to each dot could be mapped to a number from 1 to 9. When user finger touch and leave the screen, a sequence of interrupts will be occurred. In the course of unlock pattern, different lines could result in different interrupts, and the gap could be observed between lines interrupts. For example, when user draw 4 to 1, 1 to 3, 3 to 7, 7 to 9, the interrupt amount from 3 to 7 is more than others. Also, a gap could be found at dot 1, 3, and 7. This correlation between interrupts and foreground moments motivates us to model the unlock pattern through interrupt timing analysis. Next, I show our attack workflow. The first step is reading interrupt counter through monitor proc/interrupt file. The counter corresponds to the touchscreen controller. Next is some data pre-processing. Then unlock pattern modeling. Since the length of a swipe line is related to the number of interrupts, so we cluster the swipe line by the length and the graph by the interrupt count to build the correlation. It turns out that there are 5 types of states. For inference, the first step to infer a single state. Even for a single user, the way of swiping a line is different from time to time. So it forces us to build a general model instead of a simple linear equation. So we carried out a user study and built a Gaussian-like model to get this relationship. The last is state sequence inference. The state in a pattern is not independent and affected by the previous one. For example, when user have draw 4, 1, 2, 3, the next possible patterns have been limited. So we treat it as a process of slowing hidden Markov model. That is, to get the state sequence through the observed sequence. That is the amount of interrupts occur. After we get the state sequence, the pattern password could be obtained easily. In our experiment setting, we target the impossible patterns. Also, without training a specific pattern in advance, is different from previous work, which only focused on a very small set. We use 5 users to get the length interrupt relationship, that is the Gaussian-like model. And we invited another 2 users to join the testing phase. In total, we obtained 116 password patterns from each user. First, in this part, we evaluate whether the interrupt time series could be segmented successfully, or the gap search success rate. The results show the success rate is quite high. One thing we need to notice is Even the user only know how many swipe lines are contained in a pattern, the search space has been substantially reduced. Next, we evaluate the success rate for state sequence inference. I will only show one example, that is the 3-gram patterns. If we were allowed to try 40 times, we could reach 90% success rate. Even in the tough case, we only could try 3 times. Random guess only could achieve 0.0157 success rate. However, our attack could improve up to thousands of times, that is 20% at least. Okay, let's say another case is the inference application running in the foreground. The information of the foreground application is considered sensitive. If leaked, a malicious application could launch phishing attacks. For example, when a user starts an e-banking application, if the malicious application identifies it could pop up a phishing window to cover the current UI to force the user to input his password. So it's quite dangerous. In the low level, the foreground UI is continually refreshed when loading. That is the start of the application. In the example of the popular file sharing application, Share8, it first shows his splash window, and then his UI gradually transmits to his main activity with fading in animation. In the course of UI refreshing, display server system, or DSS, keeps notify the Android system through sending interrupt request, that is the vsync signal, for smoothly UI processing. Our observation suggests different UI layout and refreshing strategy will result in different interrupt time series. This picture shows the DSS interrupt patterns of 6 application learning processes, including system pre-installed application, e-banking application, and security application. We could find even we just use human eyes, this pattern could be told apart easily. This phenomenon motivates us to model the UI refreshing process through interrupt timing analysis to identify the foreground application. For time limitation, I will skip the evaluation of this attack and only give the high-level idea. Okay, let's summary. In our work, we propose a new attack. We find a new attack surface in the interrupt handling mechanism, that is the public perk interrupts file. And also, we propose a general approach to launch inference attack, that is inference timing analysis. As showcases, we give 2 concrete inference attacks to against the users, unlock pattern, and application, and identify application running in the foreground. As defense, fine-grained access control could be deployed and or decreasing the resolution. Okay, thank you for your time.
Any questions for the speaker? Okay, well, this is interesting work. Where do you see this going? Are there other side channels that are related to hardware that you think could be exploited to infer things like passwords or application use or location, things like that?
In my opinion, I think there surely exists other side channels. Just like in perk file, there have been found several channels launch inference attack, but we still need an automatic method to find such channel. Yeah.
Hi, John Stallworth, University of Illinois, Chicago. So is this attack completely eliminated if you get rid of the proc system, the /proc system?
Yeah, it lies in the perk system.
There's like no other kind of way that you can get this information out that you can think of off the top of your head?
Other method to get such information? You mean?
Getting information that would be sufficient to do this attack.
Sorry, you mean OVD?
I'm just saying without the proc system,
Yeah,
because the proc system gives you this delayed information
yeah.
that you would have difficult monitoring, say, with another process or something watching at things, right?
Yeah.
Okay, thank you.
Sorry. Okay, we could talk offline.
Peter Aldis, University of Utah. Are there legitimate uses for /proc/interrupts for individual apps, or is this just something that shouldn't have been surfaced apps in the first place?
Sorry, could you say again?
Is there any good reason that an individual application rather than the Android-based system should be able to access /proc/interrupt?
Such information is mainly designed for the debug usage, but it's surely used for some applications such as loading balance. But they are, most of them are system-level applications.
Thank you.